Hello, everyone. Today, we are going to talk about deep field video stabilization. It's the first unsupervised DNN-based framework that fuses sensor data and image content for video stabilization. It takes the video and sensor readout, such as gyroscope, as input, uses the network to run motion estimation and compensation, and finally, outputs stabilized videos. The motivation for this work is twofold. First, image-based methods produce impressive depth adaptive results. However, they suffer from artifacts such as distortion and wobbling. They usually rely on optical flow or feature tracking, which is time-consuming. They are also error-prone to dynamic scenes with moving foreground and bad illuminations. For ML-based solutions, they often require non-trivial data for training, such as synchronized, unstable, and stable video pairs. On the other hand, sensor-based methods do not suffer from artifacts. They are robust to moving foreground and bad illuminations. They are also efficient and can run in real time on smartphones. However, they only stabilize motions at the infinity plane. We present the deep field video stabilization framework that addresses the concerns above and draws benefits from both ends. On one hand, we use gyroscope data to extract the real camera motion. These real camera motions are stored within timestamps so that we can query a pose from an arbitrary timestamp. On the other hand, we also extract the optical flow from the input videos. Please note that we remove the OS translation so that the input to our model contains only the camera and object motions. Also, the optical flow can be extracted efficiently from a dedicated hardware in a smartphone's video processing pipeline. We then fuse this to information and feed them into the network for the stabilized virtual camera pose. Specifically, the optical flow is mapped to a low-dimensional feature space through encoder layers. We then extract the real camera motion within a time window from the past and future 10 frames. The motion for each frame is represented by a 4D coordinate, and we extract the rotation difference between them as the motion representation. Next, we concat the motion representation and the image feature together and feed them into LSTM. The LSTM then maps the input to a virtual camera pose. We have carefully designed the losses to control the virtual camera smoothness and how well it follows the true motion. We also save the virtual camera poses and loop them back to the LSTM as well.
In summary, the full motion representation contains three parts: the optical flow from video frames, the real camera pose history from the gyro sensor, and the virtual camera pose history from the network's output. The whole network can be trained without any supervision. Please refer to our webpage for more details. We now show the results and the comparisons. Our method produces more stable motion compared to the state-of-the-art approach. Unlike image-based methods that suffer from distortion, wobbling, and other visual artifacts, our results are artifact-free. For near-steady scene, our results are more stable as if the videos are captured on a tripod. Our method is also robust to scene with parallax. For challenging motion, such as running and driving, our method is more robust and can generate more stable results. In conclusion, we present the first DNN-based solutions that fuse sensor and image for video stabilization. It's fully unsupervised and produce stable and artifact-free results that outperform the state-of-the-art. Thanks for your attention. Please refer to our webpage for more details and results.